Hi everyone. The question says the height of a helicopter above the ground is given by h equals 3.10 t cubed. The height of the helicopter, the position in the vertical direction, is given by h equals 3.10 t cubed. What's so special about this equation? It is telling you the height as a function of time. If you were to plug in 0, the moment you start counting time, where is the helicopter? H equals 0. 3.10 times 0 is going to give you 0. So the helicopter is on the ground, right? Then you can plug in 1 second, then you can plug in 2 seconds, 3 seconds, and you're going to see the position as a function of time. You're with me so far? Very good. Now, in addition to giving the height, you're also given the time. At t equals 1.9 seconds, the helicopter releases a small mailbag. So at t equal to 1.9 seconds, the helicopter releases a small bag. So far so good? Okay, so how can you combine these two information? At t equal to 1.9 seconds, you are releasing the object, right? By plugging the time, you can determine the height of the helicopter at that time. At 1.9 seconds, you can determine the height of the helicopter. When I say the height of the helicopter, that's also the initial position of the package. The package, the mailbag, is inside the helicopter. So the moment you plug in your time, you will determine the height at which the mailbag is released. So when you combine these two information, you're going to get the initial position. The initial position is the height at t equal to 1.9 seconds. Plug in 3.10 t squared 1.9 squared, that's going to give you x sub I. That's your initial position. Tell me, what is the final position? The mailbag or the package is going to hit the ground, so x sub f is going to equal to 0 meters. Very good. So you have one-dimensional motion, you have 1D motion. Let's continue reading. How long after its release does the mailbag reach the ground? What are we calculating? We're calculating the time it takes for the package to reach the ground. We're looking for delta t. Which equations are we going to use, everybody? You have your equations, the three linear equations. What are we solving for? We're solving for the time. So only equation number 1 and equation number 3 are applicable to the problem. What is wrong with equation number 1? So at this point, we don't even know the initial velocity, but you also don't know the final velocity. When I say to you the final velocity, that's the velocity just before the impact. Don't tell me the final velocity is 0. That is incorrect. When I say to you the final velocity, that is the velocity just before impact. So equation number 1 is not going to do. Let's move on to equation number 3. I haven't even really justified the reason why you don't use equation number 1, but let's just move on to 3. Have a look. You're given the delta x, the change in position or the displacement. Do we know the displacement? Do we know how far the object moves? Yes, we do, because we know the initial height, which you calculate from the height equation, and you know the final height. So you put down 0 minus whatever your initial height is, equal to, on the right side of the equation, you have VIT, the initial velocity times time, plus 1/2 AT squared. A is the acceleration due to gravity, and you're solving for time. The only unknown you have in the equation is the initial velocity. Tell me, how do you find the initial velocity? From position, you have the height equation. From the height equation, how can you determine the velocity? Velocity is the change in height over change in time. dh, the change in height over change in time. In other words, the derivative of the height with respect to time. What is the height? It is given to you by an equation. 3.10 t cubed. How do you take the derivative of 3.10 t cubed? The 3 is going to come down. 3.10 followed by t and minus 1. 3 minus 1, that's going to give you 2. So you have 3 times 3.10, which will give you 9.30. T squared is what? The velocity. Now, if you plug in the same time that is given to you, the time the package is dropped, you can determine the initial velocity of the package. Guys, some of you are thinking, the initial package is 0. The initial velocity is 0. The initial velocity of the package is not 0. The package is inside the helicopter. If the helicopter is moving, the package is also moving with the helicopter. The moment you drop it, it has the same velocity as the helicopter. What is the velocity of the helicopter? d dt of the height of the helicopter. Okay? Velocity of the helicopter, and since the package is inside the helicopter, you will also have, this is also equal to the velocity of the initial velocity of the package. So all of this, plug in your time, get your initial velocity, plug it back into the equation, and you solve for the time. Have a look at the equation. You have 0, the final position, minus the initial position, the initial height of the package, which is the same height as the helicopter, equal to VIT plus 1/2 AT squared. You have to plug in the initial velocity of the package by taking the derivative of the height, plugging in the time, and you solve for time, correct? Good. Now again, the form you're gonna have is AT squared plus BT minus C. You have to use a quadratic equation. Have a look at problems number 1 and 2, and you will know exactly what I'm talking about if you are struggling here. Pause the video. You have your delta x, VIT plus 1/2 AT squared. You're going to have the equation in the form AT squared plus BT plus C equal to 0. And then you solve for the time using the quadratic formula.